Okay, so thank you for the introduction. Hello, my name is Tom Steinmetz, and I'm a first-year PhD student at SAMK Torun in Poland. And in December, I started my PhD work in the study of stellar mergers and specifically luminous red novae. So these are a class of transients that are typically produced by stellar mergers. So as this is quite a niche field, I'm going to first provide an overview of this topic. So luminous red novae, also known as red transients, intermediate luminosity optical transients, are well known now to be produced by stellar mergers. And the way we characterize these from classical or supernovae is firstly from their luminosities, as the name suggests. They have intermediate luminosities of 10 to the 6 solar luminosities. And just after the stellar merger process occurs, the remnant star that is produced. So it's important to note that the star that is produced in red novae are typically evolved, they appear to be evolved stars. And these cool down to very low temperatures, down to around 2000 Kelvin. And as a result of this, we get very high dust formation, molecular gas, and therefore get strong molecular emission in our optical, infrared, and submillimeter spectral observations. Another characteristic is the light curves and the way they evolve. So we typically see multi-peak light curves, and this is interesting in the fact that we really don't know what causes these multiple peaks. Also the fact that we see different numbers of peaks in different objects within our sample. So it's not really, it's a very poorly understood aspect of this field. And the final crucial difference between red novae and, for example, supernovae is that the nova is not powered by nuclear reactions. It's not powered by the decay of our process elements, but is instead powered by the accretion of gas onto the remnant of the merger. So in terms of red novae that we already know about, we have 5 in the Milky Way, the most famous being V1309 Sco, shown on the right, known for this incredible light echo. And this really kick-started the field of observational study into red novae. So it erupted in 2002 and was noted to have these strange characteristics that separated it from a classical nova. But we have 4 others in the Milky Way: V1309 Sco, which erupted in 2008, V1309 Sagittarius, erupted in 1994, CK Vul, which is it's the oldest in our sample and actually erupted back in the 17th century. And so the records of that from contemporary astronomers are quite detailed. And also Ogle 2002 BOG 360. As well as this, we have multiple red novae that have been detected in nearby galaxies, but these are quite difficult to study. We cannot study them in the same detail as, for example, V838 Monocerotis. And so really all we do for those extragalactic red novae is monitor the light curves, for example. And so that's what I show on the next slide, example of light curves of multiple red novae. You can see these multiple peaks. Some have multiple peaks, such as V838 Mon on the left, whereas, for example, V1309 Sco just below it actually seems to have just one main peak. So what I'm trying to show here is that basically the light curves are not consistent across the sample. There is clearly very complex physics going on at different levels within each of these objects. And so the physics that we're interested in is firstly the mass loss in stellar mergers. So stellar mergers are sites of significant mass loss, but the mechanisms themselves are not well known. So do we lose mass via, for example, the second Lagrange point? Do we lose it through outflows or jets? Another part of red novae that we need to understand is how the angular momentum is conserved. You have a lot of angular momentum within a binary system. And when it converges into a single star, is that angular momentum, for example, stored within the remnant star, which would give rise to stellar rotation, winds, possibly magnetic fields, or is it dispersed in the mass that is lost, which might give rise to circumstellar disks or tori? And finally, we want to understand the merger event itself and how we can derive the nature of the progenitors of these red novae purely from observations of the eruption and also of the remnants. But this last point I need to stress is quite difficult with current instrumentation. So after an overview of Reddit's novae, I need to talk about what is special about V1309 Sco within our sample. Why are we so interested in this object? So the key answer to that is that certainly in our galactic sample, it is the only object where we managed to get direct observations of the progenitor. So we were very lucky that there was a Polish astronomical survey called OGLE, which managed to catch the progenitor of V1309 Sco in its field of view for several years before the murder event took place. So you can see this curve in green. We have this vast quantity of photometric data where we are able to observe the binary progenitor. And as a result of this, we are able to analyze the light curves and determine the nature of the progenitor. So we find that it's an eclipsing contact binary with masses of 1.2 and 0.6 solar masses, consisting of two subgiants. And crucially, we're able to derive the orbital period at different epochs. And this is the curve shown in orange. So you can see this exponentially decaying trend in the orbital period. And so really, this is the first direct detection that we have of a binary system spiraling in towards each other just before emerging events. This was a really significant discovery in establishing that red novae are direct results of stellar mergers. We're also able to observe the common envelope phase. So this is when the binary system loses enough mass that the gas that has been lost basically envelops the binary system as it merges. And this is the gas that also ends up accreting onto the system and powering this, this eruption. So how does ALMA factor in? Why are we using ALMA to observe this object? So as I said before, red novae, are very dusty objects. We need to be able to probe through this high dust content to see the remnant and see the circumstellar environment. So what we did for V1309 Sco was observe it at two epochs in band 7. So we observed in 2016 and 2019. So the key differences between the epochs, as you can see in the table on the right, is that we have a very slightly different frequency range. So we shifted the spectral windows down by about 2 gigahertz. And the key difference clearly is the much longer baseline. So from 460 meters to over 3.5 kilometers, that gave us a much higher angular resolution, a much better UV coverage. And we also obtained a better spectral resolution as well. So we think that this second epoch is able to reveal a lot more detail about the structure and the properties of V1309 Sco. And so this really is the objective of the project, is to monitor the evolution of V1309 Sco, if there has been any, between 2016 and 2019. And I also want to stress that this paper, Kaminsky et al. In 2018, presents very nicely all the Epoch 1 data. So for more information on the observations from 2016, that's where you would want to go. So here I show the spectrum for both epochs compared to each other. So epoch 1 in black, epoch 2 in blue. And as you can see, we are dominated firstly by the CO3 to 2 transition. It's by far the strongest line we see in either epoch. But in terms of the number of lines that we see, we are actually more dominated by sulfur dioxide. So we detect 19 individual lines of sulfur dioxide across the spectrum. And this region on the right is purely a molecular blend of many of these lines, as well as possibly a contribution from HCO+ in one particular feature. But this is somewhat ambiguous at the moment. We need further analysis and further observations in order to determine whether this is in fact the case. But as you can see, we detect other species as well. So isotopologues of silicon oxide, sulfur monoxide, and aluminium oxide as well. And another key thing about this plot is that you can, even without detailed analysis, already see some form of evolution in certain species. I've already mentioned the possible contribution from HCO+, but we also see this brightening of about 26% in carbon monoxide, which is quite important, as I'll explain in a minute, for future ALMA observations for this object. So the main approach that we've taken so far is basically building up a full radiative transfer model. The way we did this was use a software called Cassis, which was developed by a team in Toulouse, to use Monte Carlo multi-chain methods to perform a chi-squared minimization of the 19 SO2 lines that we detect. And from the results of this, where we get values for column density, excitation temperature, line widths, and velocities of the gaseous components, we can use this to build a full radiative transfer model for the spectrum that we detect with ALMA. And so in red, I show the currently best fitting model that we have, although again, I must say this is a work in progress. We see that the SO2 features are very nicely fitted, but certain features such as the sulfur monoxide and aluminium oxide blend, less so. And there's more work that needs to be done on this to get an accurate representation. In terms of the initial results we have though, a couple of these I've already talked about. We have the detection of different species between the epochs, mainly due to the frequency shift rather than better sensitivities. We have this increase in flux in CO. One interesting result is the non-detection of HCN. So the context to this is that in epoch 1, there was a possible contribution from H13CN in one of the SO2 features, which would have been very unexpected in this object. It's a very oxygen-rich environment. And the fact that we shifted these frequencies down, we were able to cover this HCN line, and we basically find a non-detection. So as a result of this, we're able to conclude that fairly confidently HCN is not present in this object. But really the key result that we have found so far from our data in epoch 2 is this velocity gradient. So on the right, I show moment 1 maps from epoch 1 on top and epoch 2 on the bottom of the CO3 to 2 line. So the blue box also shows the relative field of view of the panel. So this is just to make sure that it's understood that we have a much smaller beam size and obviously as a result, much better resolution, as I've said before. And with our better angular resolution, we are able to resolve this really nice velocity structure where we see that the northeast section of the remnant is redshifted towards us, redshifted away from us, and the southwest blue shifted towards us. So the key thing about this is that basically this structure is remarkably similar to another galactic red nova. So this is very similar to V1309 Sagittarius. And the analysis of the velocity field in that object found that the structure after modeling was consistent with a wide angle bipolar outflow rather than, for example, a circumstellar disk or well collimated jets. So although we need to do more detailed modeling with this data, we need to do more analysis. We are feeling like the evidence is starting to point towards this consistent picture between V1309 Scorpii and V4332 Sagittarius, where they are actually contributed to by a wide angle bipolar outflow, although we need to also quantify to what degree that it contributes to potentially the mass loss in this object.
3 minutes.
Thank you. So in terms of our future plans, we want to, as I said before, we want to further tune our radiative transfer models to better reproduce the full spectrum and parameterize the physical properties of the different species. We want to model the velocity field to determine exactly the process responsible, whether this is indeed a bipolar outflow or whether there could be contribution from other mechanisms as well, such as possibly a disk or torus. We intend to submit proposal for cycle 9 with even larger baselines so that we can get a better resolution, better resolve, for example, these outflows, and possibly better resolve as well the spectral feature that I talked about with HCO+, so that we can possibly get a better determination of what is contributing to this change in the spectrum. We had a proposal accepted with VLTX Shooter, where we will, over the next 2 years, be getting optical observations with for V1309, V1309 Sco, and V1309 Sagittarius. So this will be able to observe wide molecular bands that we typically see in the optical for red novae, and especially with V1309 Sco, we'll be able to see how the optical spectral evolution is similar or different to V1309 Sagittarius, because as I mentioned, these seem to be very similar objects. And finally, we will eventually aim to publish a memo and a paper summarizing our results once we have finished our analysis. So just a very quick summary. So stellar mergers are responsible for luminous red novae, which are rich in molecular gas and dust. They are somewhat chemically peculiar. We see these, for example, metal oxide bands in the optical that we want to observe. We see this evolution in our ALMA spectrum. V1309 Sco is an important source of information and is considered a bit of a Rosetta Stone in this field due to the observations of the progenitor and this chemical abundance that we are unsure about, as well as the parallel evolution we seem to see with another red nova. And hopefully future ALMA and also combined with optical observations are expected to reveal further details about the evolution and also the kinematical structure and properties of this red nova remnant. So thank you very much.
Well, thank you very much to you for this impressive talk. I'm very impressed that we can witness such events in the zoo of stars. So we already have questions in the chat.
Yeah, thanks very much. That's very interesting. There's one question about the HCN. So if you have any possible or potential explanation for the absence of HCN, and also if you cover any HNC lines.
Sorry, can you repeat about the HNC?
If you covered any HNC lines in your setup.
Yeah, so sorry, I probably should have not stopped sharing. So if I go back to spectrum, so in terms of this, we in terms of HNC.
Sorry, you still need to press play. We
yes,
don't see. Thanks.
Yeah, sorry about that. So in terms of the absence for HCN, the absence of it is not unexpected. The part of the confusion is that we have this SO2 feature close to 345 gigahertz. And from the Epoch 1 radiative transfer modeling, there was some ambiguity about whether there was a contribution for H13CN. And so really this was causing a lot of confusion when we compared this to kind of what we expected from the chemical synthesis models that have been produced in literature. So really, in terms of the explanation of why it's not there, I'm not an expert on the chemical synthesis models, but the way I understand it is that we don't expect HCN in great quantities in cool environments that are oxygen rich. So that would really be my main answer to that. In terms of the HNC, we do cover HNC lines, but in our radiative transfer models, we don't see them replicated at all, and we don't really expect them. So they weren't a line we were particularly looking for or expecting in this spectrum.
Thanks. There's another question regarding the line fitting of the lines. So the lines have Gaussian profiles, which are fitting, but yes. Due to the expansion movements, one would maybe expect a different kind of line profile. So is this taken into account in the fitting?
Unfortunately, it's certainly something we consider, and it's one of the main explanations for the poor level of fitting, certainly in the panel on the left. Unfortunately, with the software that we are using with Cassis, the only profile we're able to fit with is Gaussian. So that's really one of the limitations at the moment. So the way that we would possibly resolve this is consider the addition of a third component, which would hopefully enable us to better fit, for example, the red wings of the lines. So as you can see in what is the 29 SIO line at 343 gigahertz and the SO aluminium oxide blend at 344.5 gigahertz, you can see that the red line doesn't properly fit the red wings of these lines. And hopefully the introduction of a third component to our model would be able to better fit this part of the spectral lines. But yeah, it's definitely a limitation that we are basically trying to model Gaussian profiles to non-Gaussian spectral lines.
Fair enough. Well, limitations of the software.
Yes, yeah.
There's another question about what the physical process powering the outflows is in this kind of systems.
Powering the outflows, did you say? Sorry.
Yes.
Yeah, so this is something that is quite ambiguous. So firstly, we're not even entirely sure that there are outflows for a start. Really, in terms of the processes, this could partly be due to magnetic fields from stellar rotation, say if the angular momentum is stored within the remnant. But if I go back to the slide where I talk here, there are so many ambiguities that we can't really produce a conclusive picture of the powering of these outflows, simply because we're not entirely sure if the conditions are correct. And even from our observations, we are not exactly sure that these are outflows yet. And this is hopefully what we will uncover with the more detailed analysis of this data set, and hopefully with further ALMA observations with much better resolutions, where we can hopefully resolve these outflows to a higher degree.
Okay, thank you for all these answers and very nice observations and talk.